Alright, here we have lecture 2.5, which will correspond to section 3.3 from the textbook. Highly recommend you read that section 3.3. It covers a lot of interesting and important information. But the topic for this lecture is fairly short, and so we're going to discuss average rate of change. Now, I can't stress the importance of this topic because this average rate of change, once you implement a limiting process, gives you the derivative, which is one of the most important concepts in all of science. You'll cover that in detail in Calculus 1, but it all starts here with average rate of change. So before telling you how to compute average rate of change, I'm confident that you already know how to do it. So let's go ahead and explore that. Suppose you got a man jogging around a 200-meter track with his friend. His friend records the following lap times. Compute average speed per lap. So let's start with lap 1. So in lap 1, it's basically, speed is change in distance, and that little triangle means change in distance divided by change in time. We compute that change with subtraction. So at the end of the first lap, he has traveled 200 meters, but when he started, he was at 0. And at a distance of 200 meters, he'd been jogging for 32 seconds, and of course, at a distance of 0 meters, he had been jogging for 0 seconds. And when we compute that, let me see here, we get 6.25. So he had a speed of 6.25 meters per second. Now let's look at lap 2. So lap 2 begins, or I should say ends, when he hits 400 meters, but lap 2 didn't start until he was at 200 meters. And then we have the corresponding time values. So that was 68 seconds at the end of lap 2, but he was already at 32 seconds at the beginning. So in other words, lap 2 still took 200 meters. Each lap is 200 meters, but lap 2 took 36 seconds. So a little bit slower. So when we divide, we get 5.5 repeating meters per second. Now, I want to stress, he's not a robot. He's not running at a constant speed. If you've ever been jogging, you know you're not going to be running at a fixed speed the entire time. So you have little differences in your pace. Sometimes you're speeding up, sometimes you're slowing down. When we look at just the start and end points and use those, we're actually computing the average speed. So you can see his average speed in lap 2 is a little bit slower than his average speed in lap 1. And let's look at his last lap, lap 3. So lap 3 concludes at a distance of 600 meters, but starts when he's already ran for 400 meters. Remember, each lap is 200 meters. And at 600 meters, he's been running for 108 seconds. And that lap started at a time of 68 seconds. So we compute that. We get, I believe, 5. Yes. So his average speed for lap 3 is 5 meters per second. So it definitely appears that he is slowing down. So let's go ahead and abstract what we just did. If we abstract what we just did, we get the following definition. Average rate of change over some interval is this change in y divided by change in x. So for average speed, we're just dividing change in distance divided by change in time. And again, we're only looking at the endpoints over that interval, right? So if we're trying to figure average speed in a lap, all we need is when that lap started and when that lap ended. We don't need any data during the lap to actually compute the average speed. For example, suppose, I was driving from Savannah to Atlanta, and let's just say it was a 300-mile trip, and let's see here. And suppose it took me 4 hours. Well, let's say 4.5 hours. So if it took me, 4.5 hours to go 300 miles, then you can just divide and you get 66.6 repeating. Well, that would tell you my average speed was about 66 miles per hour. Anywho, let's go ahead and look at this example. So over this interval, you can kind of think of this as your A and B. So it's just going to be f at 3 minus f at 1 divided by 3 minus 1. So it really matters that they stack over each other. So if we do f at 3 minus f at 1, we have to have 3 minus 1 in the bottom. So the denominator is pretty easy. That's just 2. Now f at 3, that's just inputting and evaluating a function value. So when we plug 3 into the function, if you need to, you can go off to the side. F at 3 equals, plug it in, 3 times 3 plus 1, which is 10. And if we evaluate f at 1, that's 3 times 1 plus 1, plugging it into the function, and we get 4. So that's 6 divided by 2, which is 3. And now let's go ahead and evaluate the same average rate of change, but over a different interval. So over here for problem 2, it would be f at 100 minus f at negative 3 divided by 100 minus negative 3. You can think of the negative 3 as your A and 100 as your B, and just use the formula from above. So when we evaluate f at 100, we get 301 minus f at negative 3 gives us a negative, 8. And then we have 100 minus negative 3, which is 103. Type that into your calculator. And, surprise, surprise, you get 3 again. Well, that's because if you look at this equation, some of you may notice your slope-intercept form, function f is a line, and lines have a constant rate of change. So lines have a fixed rate of change. They never speed up and never slow down. They always move at the same rate. So the average rate of change will always be the same. It doesn't matter what two x values you pick, the average rate of change for this function is always going to be 3 because it's a line. Now let's look at a nonlinear example. So here in this next example we have function g. So if we want to compute average rate of change from 2 to 5, that would be g at 5 minus g at 2 divided by 5 minus 2. So denominator is 3. Now if you have to, go off to the side. G at 5, that's going to be 5 squared minus 5, which is 20. G at 2 is going to be 2 squared minus 2, just plugging it into function, which is 2. So we got 20 minus 2, which is going to give us 6. Now let's go ahead and evaluate average rate of change from 5 to 7. So that'll be g at 7 minus g at 5 over 7 minus 5. So that's 2. Now g at 7, you plug it in, you're going to get 49 minus 7, which is 42. G at 5, when you plug it in, is going to be 25 minus 5, which is 20. And you get something interesting here. We get 11. So you can see that this function g is definitely nonlinear. It has a different rate of change. So if we were to look at this graph, if we study it from 2 to 5, a positive rate of change or average rate of change tells us that there's a net increase. So we have a net increase from 2 to 5, and notice that the average rate of change is still positive from 5 to 7, so it's still increasing, but notice it's a bigger number. 11 is bigger than 6. What that tells us is that on average it's increasing at a faster pace. And that makes sense. If you study this graph, it's actually shaped like a parabola. And we know parabolas, as you move farther from left to right, they get steeper and steeper and steeper, indicating that they are increasing at a faster and faster rate. So that's just a useful tip. So the average rate of change doesn't tell us where it's increasing or decreasing. It just tells us if there's a net increase or a net decrease. But anywho, that is average rate of change. I've covered everything that's on worksheet 4, so you are ready to finish up that worksheet and have a wonderful day. Keep up the hard work.